I'm thrilled to introduce Pieter Abbeel. Professor Pieter Abbeel is director of the Berkeley Robot Learning Lab and co-director of the Berkeley Artificial Intelligence Lab. Abbeel has founded two companies, Gradescope, AI to help instructors with grading homework and exams, and Covariant, AI for robotics automation of warehouses and factories. Abbeel is founding partner at AIX Ventures, a venture capital firm focused on AI startups. Abbeel is the host of Robot Brains podcast, which explores what AI and robotics can do today and where they are headed, through conversations with the world's leading AI and robotic pioneers. His work is frequently featured in the press, including the New York Times, Wall Street Journal, BBC, Rolling Stone, Wired, and Tech Review. Pieter, over to you.
Hi, I am Pieter Abbeel, and wear a few hats these days, so I thought I'd start with a quick self-intro before we dive into the main topic that I'd like to talk about, which is generalizable learning in robotics. So these days, I am a professor at UC Berkeley, where I'm director of the Robot Learning Lab, and where I do teaching and research in AI and robotics. I'm also co-founder of a company called Covariant. At Covariant, we build the next generation of AI-powered robotic automation with a specific focus these days on deployments in warehouses. I'm also the host of the Robot Brains podcast, where we discuss all kinds of recent advances in AI. And I'm an investment partner at AIX Ventures, where I spend time investing and advising early stage AI-focused startups. But in this presentation, as I mentioned, I'd like to discuss some of the recent work we've been doing at Berkeley and the general vision around that work. And the thing that really excites me from an academic viewpoint is this notion of generalizable learning. And it's a notion that's been around for a little while now. For example, if you look at computer vision, for over a decade, the practice is to pre-train, for example, on ImageNet, and then fine-tune your neural network for the task you care about. And of course, these days, the pre-training happens on even bigger data sets and possibly with self-supervised learning. But the model/paradigm remains the same, pre-train on a large data set followed by fine-tuning. Same thing is true for natural language processing. Models like BERT and GPT, those are some of the early models, of course, there's many more since, train on a large body of internet text, which doesn't necessarily match the task exactly that you care about later, and then get fine-tuned on the task you care about. How about robotics? Turns out we don't have an equivalent in robotics just yet. There's no such canonical pre-training followed by then fine-tuning for a thing you actually care about. And there's no reason there shouldn't be, probably. And so what I'd like to do here is to share with you my thoughts on how we can get to such a pre-trained model. Robotics, of course, is quite different, so it'll be a little different, as you'll see. So here's the big picture of how I think we can get to generalizable robotics intelligence. We'll have data from many sources, but some data, there's a lot more of than other data. It's cheaper to get. So I think we'll have to rely about 99% on data that's directly available on the internet video, internet text. Maybe close to 1% on data a robot collects on its own, maybe in simulation of itself or in the real world. And then a small fraction of the data will be collected with active human input. And more specifically, internet video, internet text, we would run unsupervised representation learning. That would be the start of the training of our large neural network. That would be the common brain for many, many robots. We would supplement that then with unsupervised RL, where reinforcement learning happens in a way that's not task-specific, but is purely exploratory. And then finally supplement that with the fine-tuning step on the task that we might care about with human feedback or human-specified task-specific reward functions. And so what I'd like to share with you is on each of these three fronts, some progress that's been made recently that gives me a lot of hope that we can actually get this done in the next few years. Let's start with the unsupervised representation learning. The biggest chunk of data that's being processed is over there. And specifically, I'll talk about doing so from video, as that's where it's already had some very direct visual motor skill impact, but you can also think about text doing similar things. So why might you care about studying video prediction beyond the fact that maybe it could lead to this generalized robotic brain? Well, there's a lot of video data available. And usually when there's a lot of data of a certain modality, there's a big opportunity to train large neural networks to recognize the patterns in that data and do something interesting with it. Accurate prediction, accurately predicting the next frame that's going to come in a video or a sequence of next frames, requires a very deep understanding of the natural world. It, under the hood, requires effectively forming an understanding of the 3D geometry of the world, of the physics that affects the world, the motions that are natural in this world, and that there are objects and objects can interact. And so video prediction is a great proxy to make a neural network internalize these concepts. What are some other reasons you might care? Well, there are many useful applications of video prediction. For example, compression. If you have a very good video predictor, that will allow you to compress videos and now distribute videos with much lower bandwidth connections. If you're curious to learn more, I put a lecture online on that in the context of my own class at Berkeley, and that's linked here. Can be helpful in robotic control. It's been shown already in some preliminary early works that if you have a good video predictor, you can use it to plan against that to make a robot do some basic manipulation tasks. And another robotic application, of course, is driving, self-driving cars, where we've also seen in some of the Tesla AI highlights that video prediction is part of what they are doing. So, looking at the kind of practical academic research side of things, what are some data sets that we could work with? Kinetics 600 is video scraped from YouTube with 600 labeled action categories. And here are some examples of these videos. These are relatively short videos, but with a very high diversity in what happens in these videos. Another data set that's pretty common to look at is the BAIR robot pushing data set and the RoboNet data set. They're both quite similar. They essentially show robots pushing, potentially picking, dropping objects that are situated in front of the robot. So now when you think about generative models for video, just many approaches here. You could think about GANs, you could think about many other types of models. Models I've been pretty excited about are exact likelihood models or possibly approximations to the likelihood. And the reason I like likelihood models is because when you optimize the likelihood, you have a very specific number that measures effectively how good you would be at compression of the data set. And more generally, what it allows you to do by having a very specific number when you train such a model is that you can just compare the number. If you change the neural net architecture to a new neural net architecture, you can just see what is the holdout log likelihood on one with using one model versus the other model, and that way make, in some sense, fairly direct progress on getting better video prediction models. So some nice benefits of using autoregressive models is that they're stable to train. They do not suffer from posterior collapse, and they're easy to evaluate. As I mentioned, it's a very grounded metric you're optimizing. And so it's easy to compare. It's not about eyeballing which one looks better or worse. You can just look at the numbers. So what are some of the models that are doing really well? Here's one example. This one that we did in my lab at Berkeley. So in this model here, what we do is we turn each frame into essentially a vector quantized representation of the patches in the frame using a pre-trained VQ GAN. At this point, we have a discrete sequence of tokens that represents the video. And so once we have that, we can use standard transformers to train a causal model to predict the future tokens, which constitute the future frames. And so that's what we looked at here. When you do that, you can actually get some really good video prediction. Now, state-of-the-art video prediction, what you see here on the left is when we trained our neural network on the RoboNet dataset. And then in each of these videos you see play here, the first couple of frames are from an actual recording, and then all the frames that come after are predicted frames. Same thing on the right here. This is from the kinetics, when you train on kinetics. And then, again, this is actually generated by a neural network. The first few frames are presented to the neural network, and it's supposed to then complete that video sequence. And we see here 256 by 256 with high resolution for video prediction today, working quite well. Now back to the problem I talked about earlier, this notion of training a large neural network that is ready for faster learning of new things in the robotics context. So the experiment we ran here is we did a pre-training, in this case on a simulated environment called RL Bench, on a lot of videos from this environment. Then we fine-tune in other simulated environments to see if, for example, we go from RL Bench on the left, which looks quite different from RoboSuite on the right, if we get faster learning thanks to the video prediction pre-training. What we see here in these experiments is that's indeed the case. So in each of these graphs, horizontal axis is time, number of steps in the environment that the robot has to take during the learning process. Vertical axis is success, the higher the better. What we see is we see two learning curves in each of these graphs. The black curve is Dreamer V2, which is a state-of-the-art model-based reinforcement learning algorithm. The red curve is the exact same algorithm with the exact same neural net architecture, but instead of randomly initializing the weights of the neural net, for the red curve, we pre-train that neural net on video prediction on the other environment, RL Bench. And we see that this pre-training makes a very big difference in how quickly the neural network can absorb new skills that are in these other environments. So it's exactly what we're hoping for. Okay, so that's one example of some progress in the top left corner of this overall diagram. Now let's take a look at the bottom left here. So what we covered so far, we've covered the concept of pre-training on large video data sets to get a neural net ready to quickly adapt to a task. But rather than making this jump in one go from pre-training on video to adapting on a task, you could imagine an intermediate step where our neural net, our agent, also gets some time on its own that does not require human time spent, where the robot either in simulation or in the real world gets to effectively play in the environment, unsupervised play, unsupervised reinforcement learning. And the hope here would be that by doing that, it can learn about itself, because the videos it's going to watch, those videos are YouTube videos, they're videos of other robots and so forth. It's not going to get a sense of how itself works. And here it can learn about its own embodiment and its own ability to interact with the environment. And then after that, we can hopefully fine-tune even quicker. So there's been actually a good amount of work on how to have AI agents play, meaning you put them in some game or simulated environment, and the agent is supposed to just, well, play. And the question, of course, is how to formalize that. But the idea is that the agent is doing something self-directed, where there is no score provided that tells it what to do. It should just explore the environment, hopefully learn interesting things about the environment and its ability to influence the environment, and then later hopefully learn something that you task the agent with more quickly. One approach that has been quite successful, and it's probably if I were to start a new project today, is also the one I would build upon, is based on entropy. So when you think about what does it mean for an agent to play, to do undirected discovery of the environment, one way to measure whether the agent is doing that is to measure the entropy of the distribution over states that the agent encounters. The higher the entropy, the more diverse parts of the environment the agent has visited, the lower the entropy, the less the agent has explored. And so that's how we can formalize this notion of play. And so we have an intrinsic reward, which means it's not task specific, it's intrinsic to the agent wanting to explore, which is the entropy of the distribution over states visited. A little tricky part here is that measuring this in continuous spaces or high dimensional discrete spaces can quickly become intractable. So we're going to need a proxy for this that hopefully is precise enough to still measure this reasonably well. So what we looked at in great detail and have shown can work really well is to use a nearest neighbor approximator to the entropy. So the way this is done is rather than measuring exact entropy, which is intractable, we're going to measure entropy by looking at the, in this case, log of the distance between states the agent has visited. Specifically, for a specific state the agent visits, let's say state SI, we're going to look up in the dataset of states already visited, the k nearest neighbors. We're going to measure the distance to the k nearest neighbors and then compute the entropy this way. So if the agent visits a state that is very far away from states it's visited before, it's going to contribute a lot to the entropy, which is what we want. If it visits states that are very close to states it's been to before, it's going to have almost zero contribution to the entropy. And that's also what we want, because that's not what we want the agent to do. Here's a full system that you could set up this way. The agent takes in observations on the left, bottom left here. This goes into a neural net encoder. Then in a embedding space, representation space, we will start measuring this particle-based entropy, and the agent will run reinforcement learning to maximize this particle-based entropy. To make sure that this representation is a good representation space, we'll have an auxiliary loss. In our work here, a contrastive loss. You could imagine also using math autoencoders. Either way would be a good choice to ensure we get good representations here for the space in which we measure entropy, and also that we might use later for an agent to fine-tune its policy upon. Okay, and so here are a few experiments. These are DeepMind control suite tasks, so simulated robotic control tasks: cheetah run, cheetah flip backward, hopper hop, hopper hop backward, walker run, walker walk, and so forth. What you see here is, again, several learning curves. Going off to the right, the more time has been spent. Higher up is better, so the faster the curve jumps up, the better. So if you look at these curves, the green curve is the one that's doing best. That's the approach where the agent first gets to spend a small amount of time doing play, entropy maximization, and then starts optimizing the reward. The blue curve is the state-of-the-art reinforcement learning algorithm that runs directly from the beginning to optimize the reward that we care about, which is, for example, forward progress of a runner and so forth. So what we see here is that by making this small change, before we run Dr. Q, we just do a little bit of play. The learning curve shoots up a lot faster than by directly diving into optimizing the task reward. This is indeed what we hope for. We also tested this on the Atari game suite. So you see here is the last column is APT, which is our approach. Boldface means the best performance. This is after a fixed number of steps in the game. And we see that APT has the most games for which it has the best performance, suggesting that indeed it's good to do this play ahead of time. Also, by the way, the other two, the one here in front, Visor, also has some form of play ahead of time based on mutual information. Between the two of them, they dominate this table. And so it's showing that indeed play can be really helpful to then learn a lot faster. All right, so we covered how to learn from the massive amount of data that's available on the internet with one example of progress, but of course a lot more to be done. We covered how an agent can play on its own, not knowing yet what the task is going to be, but just maximizing the entropy of the states it's visited. And thanks to doing so, much more quickly learn to optimize the reward we care about later. Now let's take a look at some of the challenges and interesting progress in how we do the final fine-tuning. And this can be done in various ways. You could specify a reward function that needs to be fine-tuned against, or you could decide to have a human in the loop to encourage the agent when the agent is doing well, and maybe discourage them a little bit when they're doing something that's not so good to do. What we're going to look at here is how most effectively bring the human in the loop of this learning process. And there's some reasons for this. So our agent, let's say a robot, interacts with the world, and there are consequences to those interactions. Now, if we, for example, look at the DeepMind control suite, this is humanoid. If we run a state-of-the-art reinforcement learning algorithm and we successfully maximize the reward, which in this case is measuring the x coordinate, so forward progress, which is measuring the amount of energy expended in each of the motors, the actions squared, and trying to minimize that, which is also measuring how far the center of gravity is from the 1.3 meter mark, which is the standing up height, to make sure the agent is encouraged to run to make forward progress rather than maybe try something else. If we optimize this objective here, the behavior on the left is what comes out. So even though this objective makes a lot of sense, you might still find this behavior undesirable. you might want a more natural motion, or maybe there's something else you don't like about it. And in traditional reinforcement learning, you'd have to go in and then try to come up with new descriptions in a mathematical form of what you want, which can be very hard to get right. An example from the real world is cooking. If you're not very precise about how you specify how things should be done, things can go very wrong. So a lot of eye to detail is important in the reward function. Again, very hard to get that right. And here's a video game that's become quite famous for this specific problem. In this video game, it's actually a boat race. The agent is supposed to race the other agents in this parkour here. You see the circuit. If you look carefully, you see these colored dots going around the circuit. But the AI agent is going in a circle in the harbor. The reason it's doing that is because you get bonus points for hitting certain things. And it turns out in the harbor, there's the right density of things, and you can get a higher score by circling in the harbor than participating in the race. Now, obviously, that's not the goal of the game. So the score in the game was misspecified to reflect what the designers of the game actually wanted to happen. And that's the challenge here, that very often when you start specifying a score, a reward function, it's very hard to get it right. So can we keep the human in the loop to continually allow it to give more feedback to get out what you want? So rather than putting reward directly as input to the algorithm, we're going to have a human who watches the agent in action when it's doing its repeated interaction with the environment and giving feedback. There's a couple of works that I want to reference here. Ibarz et al. And Cristiano et al. That looked at preference-based learning. And the work I'm going to present here builds on top of that work, similar ideas, but combined with some of the play pre-training, allowing for actually much more efficient results, because now the agent plays ahead of time for a while on its own with no human feedback required. And then once it's played and more ready to learn, the human gets brought in and it happens to learn quite fast. So one question is, how do we internalize the human feedback? What does it mean for a human to like something an agent did now and maybe like even more something they do later or less something they do even later? The way we formalize this is by saying if a human observes two trajectories the agent executed, trajectory sigma 1 and sigma 0, if the human prefers sigma 1 over sigma 0, then we want it to be the case that essentially this quantity here is close to 1. So what is this? This is a standard classifier. It's essentially saying there are two things. There's the reward along trajectory 1 here, sum of rewards along trajectory 1, and then there's sum of rewards along trajectory 0, as well as along trajectory 1 in the denominator. And so it's saying I'm going to look at the exponentiated rewards, and I'm going to take a softmax score, and if trajectory 1 is preferred, then the softmax score of trajectory 1 compared normalized against itself and trajectory 0 should be a high score close to 1. And so by optimizing the objective, we're essentially just training a classifier. And so that's exactly what we do. Step 1, collect samples via interactions with the environment. Step 2, collect human preferences, feedback, look at pairs of trajectories, say which one you prefer over which other one. Then a classifier is trained with the cross entropy loss from the previous slide here. And then we use reinforcement learning against the reward function that was just learned in step 3. If we're lucky, we're done. But very often, actually, what happens is you learn a reward function that is quite precise for the parts of the space where the agent has already been. But in parts of the space the agent hasn't been yet, it's not so precise. So after you optimize your policy, you will collect more rollouts. You get more human feedback, further fine-tune your reward function, and keep repeating this process till you hit convergence or the human finds its satisfactory performance. Here are some examples of the results of this in action. So what we see here on the left is a quadruped robot waving its left front leg, on the right waving its right front leg. Those are two different behaviors. And so what happened is we asked the human to do two different training sessions with two different goals. And what the human does is just compare trajectories, which two trajectories, for each two trajectories they get, which one they prefer over which other one, and that learns a reward function on the hood. And then you see that indeed two different reward functions were learned, and two different behaviors emerged. And so this is showcasing that a human can indeed teach a robot different things in a very deliberate way. Here's another example. Here, a human taught this robot to do backflips. It took only 50 queries, so only 50 interactions with the human for this robot to learn to backflip. Question you might have is, can we avoid reward exploitation this way? Like the humanoid that was running in a weird way, with human feedback, can we teach it to run in a more natural way? So here we have the walker, which is quite similar to humanoid, though not exactly the same robot. We optimize the reward function that is standardly specified for this robot in DeepMind control suite. And we get indeed forward motion and center of gravity is at a good height and so forth. But it's not the kind of running maybe that we're hoping for. So what if we now do this with human feedback, where the reward function is learned from the human feedback throughout the learning process? Here's what we get out. And we see that indeed, through human feedback, in this case took less than 20 minutes of the human supervising the robot during its learning, it can learn to run in a way that, in this case, human found more desirable. So let's take a step back again. I started this presentation saying that what I'm really excited about is to see if we can get something that leads to generalizable robotic systems, where we can have a single large neural network that is ready to learn new things quickly, just like we have already seen play out in computer vision, in natural language processing. I think this is actually possible, and it'll require a combination of different data sources to make this work. The biggest data source will be internet data, just because there's so much data there. That data will mostly teach our robot, the large neural network, that essentially the brain behind the robot, about how the world works. That won't teach it, however, how the robot itself works. So there'll be some unsupervised reinforcement learning, which will be a smaller amount of data because the robot has to actually go collect that data, or we have to run a simulator to generate that data. And in that data collection, the robot is actively interacting with the world, simulated or real, learning from those interactions and trying to get as rich a set of interactions as possible to learn more about its own capabilities inside the world. Then once we've done both of those, this large neural network will be, I expect, if we do this all really well, trained in a way that makes it extremely ready to acquire new skills very quickly. We could acquire those skills with imitation learning, so imitate human demonstrations, reinforcement learning, where we specify a reward function, or reinforcement learning, where we have a human in the loop, which I showed some examples of, that can guide the learning into the right direction so that you don't get undesirable outcomes, which can happen if you misspecify your reward function. So this is obviously still much a work in progress, not just in my lab. Many other labs are working on similar related things, but I do think this is one of the most exciting things to be working on today in kind of the academic research push in robotics. Thank you.